Hello guys, today we will discuss about the diagonalization. So basically we'll understand that what is diagonalization is all about and how do we diagonalize the given matrix and what are the steps involved in the diagonalization. So this will be the discussion of today's topic. So let us start with the understanding about the diagonalization. So here we have the diagonalization theorem, basically that the diagonalization theorem will talk about the any n cross n matrix. If I consider, say, let us consider any n cross n matrix, say A, which is diagonalizable. I say that it is diagonalizable if and only if A has n linearly independent eigenvectors. Okay. So in fact, what we are doing in the diagonalization. So usually it is basically, the simple understanding is any given matrix A, we're going to write it in terms of A is equal to PDP inverse. So here when you're actually doing the PDP inverse, it means that your P is the matrix which is having all the linearly independent columns. When I say linearly independent columns means it has all the linearly independent vectors, and P inverse is the inverse of this matrix and D is the diagonal matrix. Here D will be the diagonal matrix. Okay, so like we have some properties with respect to this. For example, we say that it is in terms of theorem that an n cross n matrix, if I have with n distinct, we can consider it as theorem only, n distinct eigenvalues, then it is diagonalizable. We say that it is diagonalizable. When I say this, it has to have the n distinct eigenvalue. Means no two eigenvalues should be same. So that's the meaning of this particular theorem. If it has n distinct eigenvalue, if it is a 3 cross 3 matrix, then it has 3 different eigenvalues, say x1, x2, x3. When it comes to the eigenvalue, we usually consider lambda 1, lambda 2, lambda 3. So if it has 3 distinct eigenvalues, then we say that corresponding matrix will be diagonalizable. Okay, so now let us understand this particular concept with the help of example. So for example, let me take up now one matrix. Say let us see that A equal to 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. If this is the given matrix, and we have to diagonalize this matrix if possible. We have to diagonalize the given matrix if possible. So if that is the case, then how one can check the diagonalization? What are the steps involved in this? The first step for this is finding the eigenvalue. Finding the eigenvalue of the given matrix A. Okay, so for finding the eigenvalue, you know that the characteristic equation is determinant of A minus lambda I equal to 0. So this is your matrix that will be nothing but determinant of a minus lambda I is nothing but 1 minus lambda 3 3 minus 3 minus 5 minus lambda minus 3 3 3 1 minus lambda, which is equal to 0. So here basically you just only concentrate on this diagonal elements and subtract the lambda from this. So it is nothing but you're taking the matrix A and taking the lambda associated with the identity matrix, then subtracting is as good as subtracting the lambda from the diagonal entries. So this you have to solve now. Okay, so this is simple. It's a 3 cross 3 determinant. You can just solve it. This will be equal to 1 minus lambda into minus 5 minus lambda, and this is minus into minus, it becomes plus 9. So minus 3 into 1 minus lambda, this is here plus 9. So plus 3 into minus 9 minus 3 into minus 5 minus lambda, which is equal to 0. And now you have to simplify this. Here you can take, this is 1 minus lambda, this is minus 5 into minus 1, so this will be plus 5 lambda minus lambda plus lambda square plus 9. So minus 3 into, here inside it is minus 3 plus 3 lambda plus 9 plus 3 into minus 9 plus 15, then plus 3 lambda, which is equal to 0. So we have to further simplify this. Here I take this is 1 minus lambda. You can simplify lambda plus 4 lambda minus 5 plus 9 is plus 4. Then here you can see minus 3 into 3 lambda plus 6. So plus 3 into 3 lambda plus 6, which is equal to 0. And here you can take, this is 1 minus lambda. This is nothing but, you can see this is in the form of a square plus 2ab plus b square. It is simply lambda plus 2 the whole square minus 3. If I take 3 out, it is into 3 lambda plus 2 here plus 3. Again one more 3 if I consider here out, it is lambda plus 2, which is equal to 0. You can observe in each term we have lambda plus 2 is out. I can take it as completely out. If I take that, here I am left with 1 minus lambda into 1 lambda plus 2, and then here minus 3 is minus 9, and here it is plus 9, okay, which is equal to 0. So plus 9 minus 9 cancels. So here you have only simply the two equations where lambda plus 2 equal to 0. You can see lambda plus 2 is 2 times you have. So therefore it is lambda plus 2 equal to 0 with multiplicity 2. Of course lambda will be equal to minus 2 with multiplicity 2. When I say multiplicity 2 means it is repeating 2 times. Similarly 1 minus lambda equal to 0 implies lambda is equal to 1. So we have got now 2 eigenvalues. So this is basically the step 1. So we have actually got the eigenvalues now. The step 2 of the diagonalization is finding the corresponding eigenvector. So finding the corresponding linearly independent eigenvectors of A. So therefore what I do is first let me take for lambda equal to say minus 2, and we are going to find out the eigenvectors. So therefore the augmented matrix will be, basically whenever we have lambda equal to minus 2 means the equation will be Ax is equal to lambda x, as we know. This implies Ax will be equal to minus 2x. This implies Ax plus 2x will be equal to 0. So it is a basic understanding. Again it implies A plus 2i times of x is equal to 0. This is nothing but my augmented matrix is A plus 2i. This is augmenting with 0. So basically I have to solve this particular equation. So this is how we are arriving at this particular matrix by using this particular method. So now let me consider a plus 2i, that is a plus 2i augmenting with 0. This is nothing but you have your a, that is 1. So I'm just adding the diagonal entry as 2. So it will become 1 plus 2. Then you have 3 here, minus 3, then minus 5 plus 2, then minus 3. Here you have 3, 1 plus 2. This is I'm augmenting with 0. Okay. Now solving it further, this is 3, minus 3, minus 3, minus 3. So 3, 3 and 3. Here we are augmenting this with 0. Okay. To do the row transformation, R2 changes to R2 plus R1 and R3 changes to R3 minus R1. So by doing this, we're getting 3, 3, and here it is 0, 0, 0, and then 3 minus 3 will be also 0. So here you can observe clearly. So from R1 we can take out R1 changes to 1 by 3 of R1. So this will give me 1, 1, 1, 0, 0, 0, and this is our final matrix after doing the row transformation. So clearly you can see your x2 and x3 are the free variables. So here there are no pivot positions, therefore they are the free variables. Hence we can write a solution as x1 plus x2 plus x3 as 0, implies x2 is free and x3 is also free variable. When you write as further solution, it is x1 equal to minus x2 minus x3, and x2 is free in the sense x2 is x2 only, x3 is free means x3 is x3 only. So when I rewrite, x will be equal to x1, x2, x3. So x1 value is minus x2 minus x3, x2 is x2 and x3 is x3. So if I take x2 out here, so this is minus 1, 1, 0, plus x3 if I consider, this is minus 1, 0, 1. So here you can see the vectors. So if I consider them, then because lambda equal to minus 2 has a multiplicity 2, you can see there are two vectors we are getting. V1 is minus 1, 1, 0, and V2 is minus 1, 0, 1. So these are the eigen vectors corresponding to lambda equal to minus 2. Now the same way we have to find out the eigenvalue corresponding to lambda equal to 1. So for lambda equal to 1, the same equation, that is ax will be equal to lambda x. So replace lambda by 1, that is ax will be equal to 1 into x. This implies ax minus x will be equal to 0. It is nothing but a minus I augmenting with 0 will be your matrix. So it is basically you are considering the matrix. A minus I is simply, it is the given matrix itself. So it is simply 1. You can take here 1 minus 1, 3, 3. So minus 3, then minus 5, minus 1, minus 3. This is, and then 3, 3, 1 minus 1. So this is the matrix which you are getting, which you have to augment with 0, 0. So now this implies you'll get here 0, 3, 3, minus 3, minus 6, minus 3. So 3, 3, 0. Okay. Now I just interchange R2 and R1, or you can change R3 and R1, you can interchange. So this will give you 3, 3, 0, minus 3, minus 6, minus 3. So 0, 3, 3. Okay. Now I'll change R2, changes to R2 plus R1. This will give us 3, 3, 0, 0. So minus 6 plus 3. Minus 3. This is minus 3. Then this is 0, 3, 3. Now R3 changes to R3 plus R2 V2 because it is minus 3. So hence we can get 3, 3, 0. So here you can observe R2 and R1. Since minus sign is there, so I'm just adding both. So here you can see minus and plus signs are there. So therefore just we're adding now the R3 and R2. That will give us the required answer. This is 0, 0 and 0. Okay, so further there is no need of doing any calculations because we are going to get the one free variable which we already wanted. We have got. So here you augment this with 0. There is augmentation with 0 is required. Okay, so all the augmentation with 0 is required. So now what we get is we can just take R1 changes to 1 by 3 times of R1 and R2 changes to minus 1 by 3 times of R2. If you do that, then you'll be getting the solution like say 3, so 1, 1, 0, 0, 1, 1, 0, 0, 0, augmentation of 0, 0. So here clearly we have the pivot positions in x1 and x2, but since x3 is free, therefore we have only one free variable. Write a solution now. x1 plus x2 is 0 and x2 plus x3 will be 0 and x3 is free. So this will give us x1 is equal to minus x2, whereas my x2 will be equal to minus x3. So therefore x2 value we can substitute here and here x3 is free. So hence we substitute the value of x2 from this. Here we can substitute x1 will become minus of minus x3, that is x3, and x2 will be minus x3 and x3 is free. So write a solution where x is x1, x2, x3, which is equal to x1 value is x3, x2 is minus x3 and x3 is x3. Hence if I take x3 out, it is 1 minus 1, 1. So this you can consider as V3. So this V3 which is equal to 1 minus 1, 1 is corresponding to lambda equal to 1. So you can just observe here carefully. This is the crucial step where you're the step 3 where you are forming your P matrix. So P matrix is a matrix where there is no need of the sequence that you have to use any sequence of writing it. Either you can use the vector which you have found, say this if I consider as V3, you can consider as, say for example, write it as V1, V2, V3, or you can write it as V3, V2, V1, any sequence is fine, or V2, V1, V3, any sequence is fine for this P, not necessary to have any kind of problem in writing the P because it has no particular the vector has to be the first. No, you can use any vector which you are taking at first. So basically the sequence will be followed by the diagonal matrix. So what usually I do is, now because the lambda is equal to 1 and then lambda is equal to minus 2 is there. So whatever you have with respect to whatever you found first, you can write it that way. So now say lambda is equal to 1 is there. With respect to lambda is equal to 1, I have got V3. So let me write V3 first. Okay. Or if you want lambda is equal to minus 2 first, then you can write V1, V2 and then V3. So let us follow that. V1, V2, V3. So V1, V2, V3 in the sense these are corresponding to lambda equal to minus 2. So write here V1. Here you can see this is our V1 and this is our V2. Minus 1, 1, 0, minus 1, 1, 0, minus 1, 1, 0, and then you have V2 minus 1, 0, 1. Minus 1, 0, 1. And your V3 is 1 minus 1, 1. 1 minus 1, 1. This is your matrix P. As I told you, there is no sequence for this. You can use any sequence. Now, when you're writing the step 4, when you're constructing the D matrix, which is the diagonalization matrix, whatever sequence you have followed here, the same sequence you should follow for constructing D. So these two vectors are corresponding to the lambda is equal to minus 2. Therefore, you should write here minus 2, 0, 0, then 0, minus 2, 0. So that means These two columns are corresponding to lambda equal to minus 2. In the sense you are supposed to use lambda equal to minus 2 as the diagonal elements. And the third diagonal element should be 1 because the third vector is corresponding to lambda is equal to 1. So whatever the sequence you are following here for P, that sequence has to be followed for D. D has to be followed by the sequence of P. But P has no sequence. So please remember that is a note step. Okay. So then now once we construct the D, the final thing is, instead of constructing the, I mean, P inverse. So just you can check AP, because you know that A will be equal to PDP inverse. Instead of finding the P inverse and then multiplying all the three and checking whether our diagonalization is proper or not, instead what we do is we can check A into P, which is equal to P into D. So if you check A and multiply with P, and then you can take P and multiply with D. If both are equal, then our diagonalization is correct. Let's check that. Now we will take A and we'll multiply that with P. So our A is known to us, that is 1, 3, 3. Then you have minus 3, minus 5, minus 3, then 3, 3, 1, which is multiplied with P. P is minus 1, 1, 0, minus 1, 1, 0, then minus 1, 0, 1, then 1 minus 1, 1. So this is, you have to multiply. So 1 into minus 1 is minus 1, plus 3, plus 0, then minus 1, plus 0, plus 3, to this row with this column, that is 1, minus 3, plus 3. Similarly, minus 3, minus 5, 0, then minus into minus is plus 3, this is 0, minus 3, minus 3, plus 5, minus 3. So minus 3, plus 3, plus 0, minus 3, plus 0, plus 1, 3, minus 3, plus 1. So now, when you write a solution, this is 2, 2, this is 2, minus 8, this is 0, and this is, this is minus 1, then this is 0, minus 2, this is 1. Okay, now let's see the PD. P into D. We have P, that is minus 1, 1, 0, minus 1, 0, 1, 1, minus 1, 1, and D is, your matrix D will be minus 2, 0, 0, 0, minus 2, 0, 0, 0, 1. So let's multiply this now. This will be equal to minus 1 into minus 2 is 2, then 0, plus 0, then you have 0, then this is plus 2, plus 0, then this is 0, plus 0, plus 1, then similarly you have minus 2, plus 0, then this is 0 again, this is 0, plus 0, plus 0, then you have 0, plus 0, minus 1, this is 0, plus 0, plus 0, this is 0, minus 2, plus 0, this is 0, plus 0, plus 1. I think we have got the answer. This is the 0, minus 2, 1. So I think here we did a small mistake, I feel. Yeah, it has to be minus 2 because This has to be plus 3. Yeah, this has to be plus 3. So therefore, we have to get this as minus 2 here. Okay, so you can see your AP and PD are equal. So therefore, AP and PD are equal. It says that the diagonalization is the diagonal. So we have completed the diagonalization. This is the last process. So this is how we are going to solve the examples. So basically what we did is there are 4 steps. The first step is finding the eigenvalue and then finding the corresponding eigenvector, and then once we find the eigenvector, then we construct the P. As I told you, P has no sequence, so you can use any sequence for P, and then you construct the D. As you follow the sequence of P, you're going to construct the D by using the eigenvalues. And once you find the D, then finally you are writing AP and PD. Then just check whether AP and PD are equal or not. This is how the process of diagonalization follows. So not necessarily every matrix has a diagonalization. So maybe in the next example we will see for some matrix the diagonalization is not possible, how it is not possible, and how exactly we will go with those things that we will be discussing in the next example. Till then, take care guys. See you all in the next video.